In this video, we will be talking about the chain rule. Let's review the topic of composition of functions. Recall that a function h of x is a composite function if you can write h of x equals f composed with g of x, which is equal to f of g of x, where f and g are two non-identity functions. If you didn't know, the identity function is f of x equals x. In other words, any input returns itself. So let's look at an example. Cosine of x squared is composite because if we let f of x equal cosine of x and g of x equal x squared, then cosine of x squared is equal to f of g of x. G is the function that we plug inside of f, so we call g the inner function and f the outer function. And we can see this here. On the other hand, cosine of x times x squared is not a composite function. It is the product of f of x equals cosine of x and g of x equals x squared, but neither of the functions is plugged into the other one. Example 1 says, create a new composite function h of x such that h of x is equal to f composed with g of x using the given functions. So we have h of x is equal to f composed with g of x. And remember, that's the same thing as f of g of x. And so we have f of, in this case our g of x is the log function. And then if I plug that into the f function, that ends up giving us the fourth root of log of x. And so here is our new h of x function. We want to do the same thing for part b. We have h of x equals f of g of x. Our g function is e to the power of x, so I want to plug that into my f function, which gives me arctangent of e to the power of x. And so there is my h function for part b. Example 2 says, given h of x, find f of x and g of x such that h of x is equal to f of g of x. So this is essentially asking, what function am I plugging inside of the other function? And so here in part A, we can see that we have this polynomial here, and then my outer function is the cosine function. So how are we going to write that? Well, g of x, in this case, would equal 4x squared minus 3x plus 12. And then my f of x function would equal cosine of x. Because again, notice that we are taking this polynomial here and we are plugging it into x. And so here are our two functions. In part b, we have that our inner function, g of x, is equal to cosine of x. And what are we plugging that into? That's getting plugged into the function f of x, which equals 4x squared minus 3x plus 12. So notice one thing that we want to note here is that in most cases composition is not commutative. What does that mean? That means that f composed with g of x is not the same thing as g composed of f of x. There is one special case where that is true, but in most cases that's not true unless the two functions are inverses of each other. So here is our final answer for part B of example 2. Now, how does this relate to what we're doing in calculus? Well, we want to take the derivatives of these composite functions. Let's see how that works. The chain rule says if g is differentiable at x and f is differentiable at g of x, then y equals f of g of x is differentiable at x, and y prime is equal to f prime of g of x times g prime of x. In other words, the derivative of f composed with g is equal to f prime composed with g times g prime. In Leibniz notation, if y equals f of u and u equals g of x are both differentiable functions, then dy dx is equal to dy du times du dx. Here's an attempt at an intuitive explanation of the chain rule. Imagine you are driving a car down a winding road. Your position on the road is the inner function and your car's speed is the outer function. The chain rule tells us that the rate of change of your speed, the outer function, is equal to the product of the rate of change of the road, the inner function, and your current speed. In other words, if you're driving down a hill, the road is getting steeper, which means that your speed is increasing. The faster you are driving, the more the road is affecting your speed. So, here's essentially how we take the derivative of a composite function. We take the derivative of the outer function and leave the inner function the same, and then we multiply it by the derivative of the inner function. So let's look at an example of that. All right, in example 3, we want to find the derivatives of the following functions. We have for part A that f prime of x is equal to, notice that this is the same function we saw in a previous example. And first we want to start by taking the derivative of the outer function, which is cosine. Its derivative is negative sine. And then I'm going to keep the inner function the same. And then we need to multiply by the derivative of the inner function, which in this case, because we have a polynomial, we would just use the power rule. So we'd get 8x minus 3, and then the derivative of 12, that's a constant, so that's 0. And here we have f prime of x. So for g prime of x, now we want to take the derivative of each of these terms. And so the derivative of the first term, let's see, I have 4 times. Now, remember in trigonometry when we write cosine squared x, that is the same thing as cosine of x quantity squared. And so in this individual term, we have a composite function in that the outer function would be f of x equals x squared, and then g of x would equal cosine of x. So I'm going to take the derivative of the outer part first. So I'm going to use the power rule. I'd have 2 times cosine of x. But I still need to multiply that by the derivative of g prime, or in other words, by cosine. So then the derivative of that would be negative sine of x. Okay, and then we have minus 3 times the derivative of cosine of x, which again is negative sine of x. And then plus 12, the derivative of 12 is 0. I'm going to clean this up a bit. So we have negative 8. 4 times 2 is 8, and I'm bringing out the negative sign. And then I have sine of x times cosine of x, and then plus 3 sine of x. So there is g prime of x. All right, for part C, we have h of x is equal to, I'm going to rewrite this as tangent of x quantity cubed, because remember that's the notation we use in trigonometry when we have exponents. And so let's identify the inner and the outer function. I've been calling them f of x and g of x. So in this case, f of x, my outer function, would be x cubed. And then g of x, my inner function, would be tangent of x, because this is what we're plugging into that function. So then if I'm following the chain rule, I have h prime of x is equal to, I'm going to take the derivative of the outer function first, and I'm going to leave the inner function the same. So I'm using power rule right now. And then we want to take the derivative of the inner function and multiply. So the derivative of tangent of x is secant squared x. We talked about that in a previous section and video. Now I just kind of want to rewrite this so that it looks a little nicer. This is the same thing as 3 times tangent squared x times secant squared x. And there is our answer for part C. All right, so for part A, we want to take some more derivatives. So f of x is equal to, I'm going to rewrite this using a power so that it will be easier to take the derivative of. This is the same thing as 3x squared minus 4x plus 6 all raised to the 1/2 power. And then if I wanted to identify the outer function, we'd have f of x, my outer function, that's the square root of x, or x to the 1/2 power. And then the thing that we're plugging into that, g of x, is equal to 3x squared minus 4x plus 6. So this is what we are plugging into our x value in our f function. So then if I wanted to take the derivative, capital F prime of x is equal to, I'm going to take the derivative of the outer function first by using power rule. And then my new exponent would be negative 1/2. And then I want to multiply that by g prime of x, which in this case would be 6x minus 4. And let's clean that up a bit. That's going to be 1 over 2 times the square root of 3x squared minus 4x plus 6. And then I'm multiplying by 6x minus 4, so I'll move that over into the numerator. Now, I'm okay with you leaving your final answer like this, but do notice that the numerator we could factor out a 2. And if we factored out a 2, that would leave us with 3x minus 2, and then these 2's would divide out. So finally we get 3x minus 2 over the square root of 3x squared minus 4x plus 6. So there's our answer for part A. All right, let's move on to part B. We have h of t is equal to e to the power of 4 times the square root of t, but that's the same thing as t to the 1/2 power plus t squared. So again, let's identify what our outer function is. F of t would equal e to some power, and then g of t, the function that we're plugging into that, notice is 4 times the square root of t plus t squared. This is our exponent that we're plugging into our t value here. So if we're taking the derivative h prime of t, then we would take the derivative of the outer function, which when we take the derivative of e to the power of t, that remains the same. So my exponent is going to remain the same. And then I need to multiply by the derivative of our inner function. So maybe off to the side here, I'm going to figure out what g prime of t is. So that's 4 times 1/2 t to the negative 1/2 power, plus if I use power rule again, that will give me 2t. And then that's the same thing as 2t to the negative 1/2 power plus 2t. So I'm going to take this and now multiply it with 2t to the negative 1/2 plus 2t. And there is our answer for h prime of t. All right, so in part C now, we are taking the derivative with respect to our x variable of secant of the square root of x. And this is all being raised to the 3rd power. So if we're thinking about this as a composite function, this is actually the composition of 3 different functions. Can you pause the video and figure out what those 3 functions are? I will go over them in just a minute. All right, so our outermost function, which I will call f of x, is equal to x cubed. Then the next function would be g of x, and that is equal to secant of x. And then our innermost function, which I will call h of x, is equal to the square root of x. So what we're doing is we're taking h of x, we're plugging that in for x here, and then that gives us the secant of the square root of x, and then we're taking that and then plugging it into x cubed to give us the function that we're looking at. So this means that we will need to take the derivative and apply chain rule 2 times. So first I'm going to use the power rule on the outermost function, and the inside functions stay the same, and I decrease the power by 1. Now I want to multiply this by the derivative of secant of square root of x. So the derivative of secant is secant times tangent. So this would be the secant of the square root of x times tangent of the square root of x. And now I need to multiply by the derivative of the innermost function, which is here, h prime of x is equal to 1/2 x to the negative 1/2 power. So why don't I move this over and multiply by that? So here I have 1/2 times x to the negative 1/2 power. And I'm perfectly fine with you leaving your answer like this. And that completes part C of example 4. For example 5a, we want to take the derivative of cosine of this quotient. Let's think about what our functions that we are composing are. So our outermost function is cosine of x. Our next function, g of x, is equal to 1 minus e to the power of x over 1 plus e to the power of x. And then our innermost function, what we are plugging into our exponent is 2x. Now, I'm going to kind of go through this and talk our way through it. When we're taking the derivative, we want to take the derivative of cosine first. So that's negative sine. And then I'm keeping the entire inside the same. Next, I want to multiply by the derivative of the next inner function, which is that quotient, so I'm going to need to use the quotient rule. So using quotient rule, we have the bottom function times the derivative of the top function. The derivative of 1 is going to be 0, that's a constant. And then I have negative e to the power of 2x. And here I need to use chain rule. And so the derivative of the function that's in the exponent would be 2. So I'm going to multiply this by 2. And then minus, so we did bottom times the derivative of the top, minus the top function times the derivative of the bottom function, which would be e to the 2x times 2 again, all over the bottom function squared. Now notice, because h of x here, if I took the derivative of that, that would be h prime of x is equal to 2. And I kind of went about it where I used chain rule in these individual moments, but notice that at the end I also could have multiplied by 2 because I could factor those out. But I chose to use the chain rule in those moments instead of waiting until the end. So again, we could leave our answer like this. I'm not going to require that you simplify that. If you did want to go about simplifying it, I'm starting to take the steps to do so. And this 2 right here and this 2 right here, I've factored it out completely, so I put that there. And then I distributed, and I can still further simplify my numerator. So notice that these will cancel out, and I can combine those like terms in my numerator. And if we did that, we get this as our final answer for part A. All right, for part B, I'm going to rewrite our function so that it's going to be easier for me to use the power rule on it. Okay, so now that I've rewritten our function using rational exponents, let's go ahead and start to take the derivative of this. So I have y prime is equal to, I'm going to take the derivative of the outermost square root, and everything on the inside stays the same. And since I'm using the power rule, I need to subtract 1 from my exponent. Now what I'd like to do is I would like to take the derivative of this inner function here. So let's go ahead and do that. I'm going to multiply this by the derivative of x is 1 plus, now at this stage, I'm taking the derivative of this thing here. So I'm going to need to use the power rule. I have 1/2. I'm keeping the inside the same, x plus x to the 1/2 power, and then I'm decreasing that exponent by 1. All right, I moved that over because I was running out of space. Where are we now? Well, I need to use chain rule again, and at this point in time, I need to multiply by the derivative of this function here. So if we do that, then we are multiplying by the derivative of x is 1, and then the last thing is I need to use the power rule on this last term here, and then I will close that parentheses and then close my brackets that I had there. Now, this is quite ugly, but again, I'm happy with you leaving your answer like this. Now, in case you were curious, if you wanted to rewrite this without using fractional exponents, instead using radicals, this is what our final answer would look like. And that's it for part B. In case you were curious, another way of writing this would be looking like this, which I thought looked really cool, and so that's another way you could have presented your answer. All right, let's move on. Okay, let's start to talk about the derivative of exponential functions. Previously, we've learned that the derivative of the natural exponential function is itself. And if we wanted to take the derivative of any exponential function, suppose a is some constant that is positive and not equal to 1, then the derivative of a to the power of x is equal to a to the power of x times the natural log of a. And notice that this even applies for the derivative of e to the x. We'd say that it's equal to e to the x times the natural log of e, but the natural log of e is equal to 1, so this formula even works for our natural exponential function. Example 6 says find the derivatives of the following functions. So in part A, if I'm just using the formula in the purple box above, the derivative would equal 2 to the power of x times the natural log of 2, and that is our answer for part A. All right, for part B, we are going to need to use the product rule since we have the product of two functions. So f prime of x is equal to the first function times the derivative of the second function plus the second function times the derivative of the first function. And the first function is a polynomial, so I'm just going to use the power rule on that. And there is our derivative for part B. All right, for part C, we have h prime of x is equal to, this is an exponential function, and my exponent is a polynomial, and so this is a composite function, so I'm going to need to use the chain rule. So I'm going to keep the exponent the same, and then I need to, because our base is not e, I need to multiply this by the natural log of 3, and then from there I also need to use the chain rule by taking the derivative of the inner function, which is in our exponent here, and that would be 4x. I'm going to rewrite this so it looks a little bit nicer. This is the same thing as 4 times the natural log of 3 times x, and then times 3 to the power of 2x squared plus 5. So there's our answer for part C. All right, let's go through part D. So I want to take the derivative of our y function, so we get that y prime is equal to. I'm going to kind of illustrate that because we're adding different terms together, I can apply the derivative to each of these terms separately. So 6 to the power of x. Notice that we're going to need to use product rule here because this is the product of 6 to the power of x times, and then I'm going to rewrite this as cosine of x quantity squared to illustrate that we will also need to use chain rule when we're working with that one. And then plus, I can factor out the 9 outside of my derivative. We've learned a theorem that tells us that that's true. And then minus the derivative of secant of x quantity cubed. We will need to use the chain rule on that one as well. So let's continue. All right, so we have y prime equals. First up, I'm going to need to use product rule. So we have first times the derivative of the second function, which is going to be 2 times cosine of x, and then I decrease the power by 1, and the inner function there is cosine, so then I'm going to need to multiply by the derivative of the cosine function, which is negative sine of x, plus the second function times the derivative of the first function, which is 6 to the power of x times the natural log of 6. On my next term, I can just use the power rule. If I bring the 2 exponent down, 9 times 2 is 18, and then I'm going to decrease the power by 1, and then finally I am taking the derivative of secant of x cubed, and I'm going to need to use the chain rule again there, so minus, I'm going to bring my power down 3, secant, I'm going to decrease the power by 1, so that gives me secant squared x. Then I need to multiply by the derivative of the inner function, so I'm applying chain rule, and the derivative of that would be secant of x times tangent of x. So here we have our final answer for part D. Finally, I just wanted to highlight a common calculus student error. Make sure to know the difference when taking derivatives like the following. What is the difference between the functions? So here we are taking the derivative with respect to z of z to the power of e. So in this case, because we're taking the derivative with respect to z, z represents our variable, and we know that e is a constant, so because I have a variable to a constant, this is a polynomial, or something that I would use the power rule on, because again, the base is a variable and the exponent is a constant. So I would have e times z to the power of e minus 1. And then here, my base is a constant and my exponent is a variable, and this is the natural exponential function, so its derivative, I would not use the power rule on it. I would just know that the derivative of the natural exponential function is itself. And so here are the differences between these two scenarios. That concludes this video. Thanks for watching.